At 06:47 hours on July 8, 1941, Senior Lieutenant Alexei Grinchik climbs into his LaGG-3 fighter at an airfield 40 kilometers west of Minsk. The aircraft bears the red star of the Soviet Air Force on its fuselage. It also bears something unusual for a modern fighter. It is built almost entirely from wood. The fuselage consists of layers of birch veneer bonded with phenol formaldehyde resin. The wings use pine and birch spars covered with plywood skinning. Total metal content: engine, armament, control cables, landing gear, and fasteners. Everything else is wood, glue, and varnish. Grinchik advances the throttle on his Klimov M105P 12-cylinder liquid-cooled engine. It produces 1,240 horsepower at 2,600 revolutions per minute. The LaGG-3 weighs 2,680 kilograms empty and 3,190 kilograms fully loaded. Wing loading is 184 kilograms per square meter. This is high for a Soviet fighter, higher than the German Bf-109E, higher than the British Spitfire Mark I. He rolls onto the runway. Takeoff speed is 145 kilometers per hour. Acceleration is sluggish. The propeller, a wooden two-blade fixed pitch unit, converts engine power inefficiently. Maximum speed at rated altitude is 575 kilometers per hour. The Bf-109F, which he will encounter in approximately 12 minutes, achieves 630 kilometers per hour. His aircraft is slower, less maneuverable, and heavier than the enemy he faces. Soviet pilots have a name for the LaGG-3. They call it the Lakarovany-Garantarovany Grob, the varnished guaranteed coffin. This name derives not from affection, but from bitter experience. The LaGG-3 kills more Soviet pilots through structural failure, fire, and poor handling than through enemy action during its first year of service. It represents one of the most ambitious attempts in aviation history to build a modern high-performance fighter without adequate supplies of aluminum. It also represents one of the most spectacular failures. The story begins not with aviation, but with Soviet industrial planning. In 1937, the Soviet Union possesses limited aluminum production capacity. Total annual output reaches approximately 60,000 tons. Of this, aviation consumes approximately 22,000 tons, approximately 37% of total production. The remainder supports construction, electrical infrastructure, and consumer goods. Soviet planners recognize that war with Germany appears increasingly likely. Such war will require enormous aircraft production. Current aluminum supplies cannot support the required output. The problem stems from geography and infrastructure. Aluminum production requires massive electrical power for smelting. Soviet electrical generation capacity remains insufficient. Bauxite deposits exist in the Urals, but transportation infrastructure to move ore to smelting facilities is inadequate. Expanding aluminum production requires years of investment in power plants, refineries, and rail networks. The Soviet Union does not have years. The alternative involves building aircraft from materials available in abundance. The Soviet Union possesses vast forests. Timber resources are effectively unlimited. Woodworking skills exist throughout Soviet industry. Traditional wooden aircraft construction techniques are well understood. The challenge involves adapting these techniques to modern high-performance aircraft requirements. Aircraft designers worldwide recognize this problem. Most nations conclude that wood construction cannot meet modern performance requirements. Wooden structures are heavier than equivalent aluminum structures for the same strength. Wood absorbs moisture, changing weight and structural properties unpredictably. Wood burns readily, making fire protection difficult. Wood deteriorates from environmental exposure, reducing service life. These limitations appear insurmountable for aircraft exceeding 500 kilometers per hour. Three Soviet designers disagree. Semyon Lavochkin, Vladimir Gorbunov, and Mikhail Gudkov believe advanced wood composite construction can equal or exceed aluminum performance. They proposed using delta wood, a material developed by Soviet chemist N.D. Kamushkin. Delta wood consists of birch veneer layers impregnated with phenol formaldehyde resin under heat and pressure. The resulting composite exhibits strength-to-weight ratio approaching aluminum while using no strategic metals. The process involves cutting birch logs into veneer sheets 1.5 millimeters thick. These sheets are dried, inspected for defects, and coated with liquid phenol formaldehyde resin. Multiple sheets are stacked with grain direction alternating in each layer. The stack is placed in a heated press at 140 degrees Celsius under pressure of 1.4 megapascals for 90 minutes. The resin polymerizes, bonding the layers into a rigid composite panel. The resulting delta wood exhibits tensile strength of 140 megapascals, parallel to grain, and 48 megapascals, perpendicular to grain. This compares favorably to duralumin aluminum alloy's tensile strength of 420 megapascals, but weighs only 60% as much per unit volume. For aircraft structures where volume, rather than weight, determines design, Delta wood offers advantages. A wing spar of given dimensions can be built from Delta wood at lower weight than aluminum for equivalent strength. Lavochkin-Gorbunov-Gudkov designed their fighter around Delta wood construction. The fuselage consists of two Delta wood shells joined at a vertical centerline. Each shell is molded in a female die to precise dimensions. Internal structure includes wooden frames, stringers, and bulkheads bonded to the shell with the same phenol formaldehyde resin. The complete fuselage weighs 321 kilograms, approximately 40 kilograms lighter than an equivalent aluminum structure. Wings use a different approach. The spars are solid pine laminated into I-beam configuration. Ribs are stamped from Delta wood sheets. The leading edge consists of plywood laminated over the front spar. The upper and lower surfaces use plywood skinning attached to ribs and spars with thousands of small nails and adhesive. Each wing weighs 193 kilograms. Total airframe weight without engine, armament, or systems, 847 kilograms. The prototype, designated I-22, flies in March 1940. Test pilot Alexei Nikishin reports generally satisfactory handling. Maximum speed reaches 605 kilometers per hour at 5,000 meters altitude. This exceeds the specification requirement of 580 kilometers per hour. Climb to 5,000 meters requires 5.3 minutes. Service ceiling is 9,600 meters. Range extends to 1,000 kilometers. These figures impress Soviet officials. The I-22 achieves performance comparable to contemporary aluminum fighters while using virtually no strategic materials. The design promises unlimited production capacity independent of aluminum availability. The Communist Party orders immediate mass production. The aircraft is redesignated LAGG-3 after its designer's initials. Production begins in June 1940 at factories in Gorky, Taganrog, and Tbilisi. The first aircraft reached operational units in January 1941. Initial pilot impressions are mixed. The aircraft handles adequately at altitude, but feels heavy in turns. Acceleration is poor. Rate of roll is sluggish. Forward visibility from the cockpit is restricted by the engine cowling and long nose. Landing characteristics require careful attention due to high wing loading and poor low-speed handling. Then combat begins, and everything changes. Operation Barbarossa, Germany's invasion of the Soviet Union, launches at 03:15 hours on June 22, 1941. The Luftwaffe destroys approximately 1,200 Soviet aircraft on the ground during the first day. Another 400 are shot down in combat. The Soviet Air Force's carefully prepared defensive positions collapse within 72 hours. LaGG-3 units engaged German fighters and bombers beginning June 23rd. The results proved catastrophic. LaGG-3 pilots report the aircraft cannot match Bf-109 fighters in speed, climb rate, or maneuverability. The LaGG-3's top speed of 575 kilometers per hour compares unfavorably to the Bf-109F's 630 kilometers per hour. Rate of climb averages 13.7 meters per second versus the Bf-109F's 17.6 meters per second. Turn radius at combat speeds exceeds the German fighter by approximately 30%. In every measurable performance category except diving speed, the LaGG-3 proves inferior. Moreover, combat reveals serious structural problems. The Delta wood construction, while strong in laboratory tests, proves vulnerable to combat damage. A 20mm cannon strike that might punch through aluminum skinning and exit cleanly instead shatters Delta wood into large splinters. These splinters jam control cables, puncture fuel tanks, and injure crew. The phenol formaldehyde resin, which binds the wood structure, proves flammable despite fire retardant additives. LaGG-3s that sustain fuel system damage burn intensely. The wooden structure provides fuel for prolonged fires that aluminum aircraft do not experience. Statistics from July 1941 demonstrate the problem. The 41st Fighter Aviation Regiment, equipped with 36 LaGG-3s, engages Luftwaffe units over the Western Front. During 23 days of combat, the regiment claims 27 German aircraft destroyed. Soviet losses during the same period: 43 LaGG-3s destroyed, 31 pilots killed. 14 aircraft are lost to structural failure following combat damage. 9 burned completely after sustaining hits to fuel systems. 12 are destroyed by enemy fire while unable to maneuver due to heavy controls. 8 crash during emergency landings after engine damage. These loss rates prove unsustainable. Replacement aircraft arrive faster than the Germans can destroy them, but replacement pilots do not. Experienced pilots killed in LaGG-3s cannot be quickly replaced. Each loss represents not just an aircraft, but months of training investment and irreplaceable combat experience. Pilot complaints focus on specific deficiencies. The heavy controls exhaust pilots during extended combat. The poor acceleration prevents energy fighting tactics. The sluggish roll rate makes defensive brakes ineffective. The high landing speed causes accidents on damaged airfields. The wooden propeller's fixed pitch means the engine operates inefficiently at all speeds except its design point, the armament. Typically one 20mm Schwack cannon and two 12.7mm Berezin UB machine guns delivers adequate firepower, but ammunition capacity of 120 cannon rounds and 200 machine gun rounds per gun proves insufficient for prolonged engagements. Engineering teams investigate urgently. They identify weight as the fundamental problem. The LaGG-3 as delivered weighs 3,190 kilograms, approximately 250 kilograms heavier than design specifications. This excess weight comes from multiple sources. Production Delta wood contains higher moisture content than specified, adding approximately 90 kilograms. The protective varnish coating, applied in multiple layers to prevent moisture absorption and combat fire, adds 73 kilograms. Additional equipment mandated after initial design, including radios, armor plate, and self-sealing fuel tanks, contributes another 87 kilograms. This weight growth degrades performance severely. Power loading increases from 2.4 kilograms per horsepower to 2.6 kilograms per horsepower. Wing loading increases from 164 kilograms per square meter to 184 kilograms per square meter. These increases reduce maximum speed by approximately 30 kilometers per hour, degrade rate of climb by 12%, and increase turn radius by approximately 18%. Lavochkin leads efforts to reduce weight. He removes equipment deemed non-essential. Radio equipment is simplified, saving 14 kilograms. Armor plate thickness is reduced from 8 millimeters to 6 millimeters behind the pilot's seat, saving 9 kilograms. Ammunition capacity is reduced from 120 cannon rounds to 90 rounds, saving 11 kilograms. The rear fuselage is shortened by 25 centimeters, saving 7 kilograms. Skin thickness in non-critical areas is reduced, saving 18 kilograms. These modifications produce the LaGG-3 Series 11. Entering production in September 1941. Weight drops to 3,043 kilograms. Performance improves marginally. Maximum speed increases to 587 kilometers per hour. Rate of climb improves to 14.2 meters per second. But the aircraft remains inferior to German fighters and continues suffering high loss rates. Simultaneously, engineers address the structural vulnerability. They discovered that Delta wood's brittleness under impact results from excessive resin content. The factory specification calls for 35% resin by weight, but quality control inspections reveal actual content averages 41%. The excess resin makes the composite too rigid. Under impact, it fractures rather than deforming. Reducing resin content to 32% increases impact resistance significantly while reducing weight slightly. The moisture absorption problem proves more difficult. Delta wood in laboratory conditions maintains stable weight. In operational service, exposed to rain, snow, humidity, and temperature variations, the wood absorbs water. Weight increases by 2 to 5% over several months. This changes the aircraft's center of gravity unpredictably. Pilots report that aircraft handling characteristics change gradually over time. An aircraft that handled acceptably when new becomes nose-heavy and dangerous after 4 months service. The solution involves more extensive varnish coating and fabric covering over all external wood surfaces. This adds weight but prevents moisture penetration. Aircraft treated with improved coatings maintain stable weight through extended service, but this treatment adds approximately 40 kilograms, negating most weight reductions achieved through other measures. By December 1941, Soviet industry begins producing significant quantities of aluminum through new smelters and American Lend-Lease deliveries. Aluminum availability makes wooden construction less critical, but LaGG-3 production continues because factories tooled for wooden construction cannot quickly convert to metal. Approximately 3,000 LaGG-3s exist in service. Stopping production would eliminate these units' fighter strength while they await re-equipment with metal aircraft. The aircraft's operational history during late 1941 and early 1942 shows gradual improvement as modifications accumulate. The LaGG-3 Series 29, entering production in January 1942, incorporates all previous modifications plus a variable pitch propeller. This propeller, designated VSH-61P, enables the pilot to adjust blade angle for optimal efficiency at different speeds. The improvement proves dramatic. Maximum speed increases to 600 kilometers per hour. Rate of climb improves to 15.9 meters per second. Acceleration increases by approximately 20%. These improvements make the LaGG-3 competitive, though not superior, to Bf-109F fighters. Soviet pilots developed tactics exploiting the aircraft's strengths while avoiding situations emphasizing its weaknesses. The LaGG-3 dives faster than German fighters due to its higher wing loading. Pilots learned to attack from altitude, diving through enemy formations, then extending at low level rather than attempting to turn fight. This hit-and-run approach reduces losses significantly. Individual pilots achieve success despite the aircraft's limitations. Alexander Klubov, flying LaGG-3s with the 31st Fighter Aviation Regiment, claims 19 victories between August 1941 and March 1942. His tactics emphasize patience and discipline. He attacks only when holding altitude advantage, fires only at close range where his limited ammunition proves sufficient, and disengages immediately after attacking rather than pursuing damaged enemies. His survival and success demonstrate that skilled pilots can overcome aircraft deficiencies through superior tactics. But Klubov represents the exception. Most pilots lack his experience and discipline. For average pilots, the LaGG-3's heavy controls, poor acceleration, and sluggish roll rate prove deadly when facing experienced Luftwaffe pilots in superior aircraft. Loss rates during the winter offensive of 1941-1942 remain severe. The 434th Fighter Aviation Regiment loses 63 LaGG-3s between November 1941 and February 1942, while claiming 39 German aircraft destroyed. The exchange ratio, while improved from earlier periods, still favors the Germans. The wooden construction creates maintenance challenges beyond combat vulnerability. Wood deteriorates from environmental exposure in ways metal does not. Glue joints weaken from repeated moisture cycling. Varnish coatings crack from temperature extremes. Wooden propellers develop stress cracks requiring frequent inspection and replacement. The phenol formaldehyde resin outgasses formaldehyde vapor in hot weather, creating respiratory irritation for ground crew working inside fuselages. Winter operations prove particularly difficult. At temperatures below -20 degrees Celsius, the delta wood becomes extremely brittle. Several aircraft suffer wing failures during high-speed flight in cold weather. Investigation reveals that low temperature embrittles the phenol formaldehyde resin, reducing impact strength by approximately 40%. The solution involves parking aircraft in heated hangars whenever possible and prohibiting high-speed flight when temperatures drop below -25 degrees Celsius. These restrictions reduce operational availability significantly during winter months. Production quality varies widely between factories. Aircraft built in Gorky exhibit generally good construction quality. Those from Taganrog show inconsistent workmanship with poorly fitted joints and inadequate glue adhesion. Aircraft from Tbilisi suffer contamination problems from improper resin mixing. These quality variations mean that aircraft with identical designations perform differently and require different maintenance procedures. Pilots cannot transition between aircraft confidently because handling characteristics vary by factory and production batch. By mid-1942, Lavochkin develops an improved version powered by the new Shvetsov AS-82 14-cylinder radial engine, producing 1,700 horsepower. This engine weighs 200 kilograms more than the inline Klimov, but produces 40% more power. The new aircraft, designated LA-5, uses essentially the same delta wood airframe as the LaGG-3 but achieves performance matching or exceeding German fighters. Maximum speed reaches 648 kilometers per hour. Rate of climb increases to 20.7 meters per second. The LA-5 proves successful, and production transitions from LaGG-3 to LA-5 during late 1942. LaGG-3 production ends in August 1942 after 6,528 aircraft are manufactured. By this time, aluminum availability has increased sufficiently that wooden construction no longer serves necessary strategic purpose. The LA-5's success demonstrates that delta wood construction can work if paired with adequate power. The LaGG-3's failure stemmed not from material choice, but from inadequate engine power relative to weight. Combat statistics for the entire LaGG-3 production run show the aircraft's troubled operational history. Soviet claims credit LaGG-3 pilots with 1,976 enemy aircraft destroyed between January 1941 and December 1942. German loss records confirm approximately 894 aircraft lost to fighters in sectors where LaGG-3 units operated, though not all these losses resulted from LaGG-3 actions. Soviet losses during the same period total 3,297 LaGG-3s destroyed or written off. Of these, 1,733 are combat losses. 819 result from operational accidents. 512 are damaged beyond economical repair. 233 suffer structural failures during flight. These statistics reveal exchange ratios far worse than Soviet aircraft like the Yak-1 or MiG-3 achieved during similar periods. The LaGG-3 represents one of the least successful Soviet fighters of the war, despite serving in large numbers for extended periods. Its wooden construction, initially seen as an innovative solution to aluminum shortage, proved liability rather than advantage. The engineering lessons proved valuable for subsequent designs. Designers learned that material substitution requires complete system redesign rather than simple replacement. The LaGG-3 attempted to build an aluminum performance aircraft from wood. This approach proved fundamentally flawed. The successful LA-5 redesigned around wood's properties rather than fighting them. The larger, heavier airframe accommodated the wood construction's weight penalty, while the more powerful engine overcame the performance deficit. Soviet industry's experience with Delta wood construction influences post-war aviation minimally, as aluminum production expands during 1943 and 1944. Wooden construction disappears from Soviet fighters. The final production aircraft using significant Delta wood structure, the LA-7, leaves factories in November 1944. Subsequent Soviet fighters use all-metal construction exclusively. The elaborate Delta wood technology, developed at enormous effort and expense, proves a dead end. Individual experiences with the LaGG-3 reveal the human dimension of technological failure. Senior Lieutenant Alexei Grinchik, who flew the aircraft throughout 1941, survives the war with 11 confirmed victories. His logbook shows 137 combat sorties in LaGG-3s. He forces lands 4 times due to combat damage, bails out twice from aircraft burning in flight, and survives 1 structural failure during high-speed dive recovery. His assessment: the LaGG-3 was a terrible aircraft that somehow got better through desperation and modification. Early versions killed pilots as readily as the Germans did. Later versions simply tried less hard to kill us. I flew it because no alternative existed. I survived through luck more than skill or aircraft capability. This bitter assessment appears repeatedly in pilot memoirs. Few veterans remember the LaGG-3 fondly. Most describe it as an aircraft they flew because they had no choice, not because it offered competitive capability. The nickname Varnished Guaranteed Coffin persists in Russian aviation history as shorthand for well-intentioned designs that fail catastrophically in service. The aircraft's combat record does include successes. 26 LaGG-3 pilots achieve ace status, 5 confirmed victories or more. 3 become heroes of the Soviet Union, the highest decoration. These men succeeded despite their aircraft rather than because of it. Their achievements demonstrate pilot skill and courage, but do not redeem the LaGG-3's fundamental deficiencies. Technical analysis of surviving LaGG-3 airframes reveals both the sophistication of Delta wood construction and its limitations. The Central Museum of the Air Force at Monino displays LaGG-3 serial number 31223, manufactured in May 1942. Examination shows excellent construction quality with precise fit of wooden components and thorough resin impregnation, but it also shows combat damage. A 20mm cannon strike to the rear fuselage created a ragged hole 30 centimeters in diameter with extensive splintering. An equivalent hit to aluminum structure would create a clean 20mm hole. The wooden structure's failure mode proves more dangerous to aircraft systems and crew. The museum's LaGG-3 weighs 3,214 kilograms empty, 85 kilograms more than specifications, and 167 kilograms more than design intent. This weight creep, endemic to LaGG-3 production, explains much of the aircraft's poor performance. An aircraft designed for 2,950 kilograms gross weight, but actually weighing 3,190 kilograms, performs as if systematically underpowered. Modern computational analysis of the LaGG-3 design confirms this assessment. Aerodynamically, the aircraft exhibits efficient shape with low drag coefficient. Structurally, the Delta wood construction provides adequate strength at reasonable weight when built precisely to specifications. The problem involved not design but manufacturing reality. Soviet industry during wartime could not consistently produce delta wood components meeting design specifications. Quality varied. Weight varied. Performance varied accordingly. This gap between design intent and manufacturing capability appears throughout Soviet wartime production. Designers created sophisticated systems assuming precision manufacturing. Factories delivered approximations of designs using available materials, tools, and workforce skills. The LaGG-3 suffered more than most aircraft from this gap because wooden construction permits greater variation than metal construction. A delta wood panel might vary 15% in weight and strength from specifications while still appearing acceptable. An aluminum panel with similar variation would obviously deviate from requirements. The LaGG-3 ultimately represents a heroic failure. Soviet engineers confronted genuine strategic crisis, aluminum shortage threatening to strangle fighter production, and developed innovative solutions using available resources. The technical achievement of building a 575 km/h fighter from wood and glue deserves recognition, but the operational reality involved aircraft that performed inadequately, suffered excessive losses, and required continuous modification attempts to achieve minimal competence. The wooden fighter program consumed resources that might have produced superior outcomes elsewhere. The 6,528 LaGG-3s manufactured represent approximately 39 million man-hours of engineering, manufacturing, and quality control labor applied to expanding aluminum production or improving existing metal fighters. This effort might have generated greater strategic value. But such calculations require hindsight unavailable in 1940, when aluminum shortage appeared to limit Soviet fighter production catastrophically. At 06:47 hours on July 8, 1941, Senior Lieutenant Grinchik takes off in his LaGG-3. He knows the aircraft's reputation. He knows its limitations. He flies it anyway because the motherland requires defense, and this aircraft is what the motherland provides. He survives this sortie. Many of his comrades flying similar aircraft do not. The LaGG-3 saves some pilots who exploit its strengths skillfully. It kills others who trusted it beyond its capabilities. This duality defines the aircraft, a desperate solution to a genuine crisis that worked barely well enough to justify its existence while never achieving the performance its designers intended or its pilots required. The varnished guaranteed coffin remains in Soviet aviation memory as a warning about the limits of material substitution and the gap between design intent and operational reality. It demonstrates that innovation alone cannot overcome fundamental deficiencies in power-to-weight ratio. It shows that manufacturing quality determines operational effectiveness as much as design sophistication. And it reminds us that pilots who flew inadequate aircraft against superior enemies demonstrated courage far exceeding the machines they flew. The LaGG-3 failed its pilots repeatedly. Many of those pilots succeeded anyway, through skill and determination that wooden construction and phenol formaldehyde resin could neither provide nor substitute.